which you recall describes the gravitational field and the electromagnetic field of a body with mass m, charge q, and angular momentum j, or angular momentum per unit mass a. Now, I gave you the metric, but I didn't give you the Maxwell field. And someone asked me, would I give you the Maxwell field, which is as it should be, because it's a coupled set of differential equations. We have to solve for g mu mu and for a mu. Sorry, I got a croak in my voice this morning. However, looking on the through the literature, it's very hard to find the a mu for the Kerr-Newman metric, but I did find a version, and this is a version known as the Kerr-Schilt form. So it's in coordinates t, x, y, and z. Z is the axis about which the object is rotating. And let's do the metric first. It can be written as eta mu nu plus f k mu k nu, where f is g r squared over r to the fourth plus a squared z squared into 2mr minus q squared. And r squared is not what you think. It's implicit in the equation x squared plus y squared over r squared plus a squared plus z squared over r squared. So in the limit as a goes to 0, it coincides with what you would normally define r to be. But when a is not 0, that's how it's defined implicitly. Now, what are k mu? The time component of k is 1. The x component is rx plus ay over r squared plus a squared. The y component is ry minus ax. Curious that there's a sign difference there, but I think I wrote it down correctly. Over r squared plus a squared. Okay, z over r. And the virtue of this form is that we can now write down the Maxwell field. And it looks like qr cubed over r to the fourth plus a squared z squared times k mu. So there you have it. The other confusion that arose, and I agree perhaps it's a little confusing, is these affine parameters that appear in the geodesic equation. This is discussed in Weinberg pages 72 and 76. And we note that in the geodesic equation, and I'm going to write it with some parameter p, we do not need to know what P is if all we're interested in is to solve for x mu. Because we can solve for x mu of P and then eliminate P in favor of T. And I'll be giving you an example of what I mean by this in a moment. And then we get x of t. And once we've forgotten x of t, we've forgotten about p. It was just an intermediate device. So when do we need to know what P is? Let me just make an observation, first of all, that g mu nu dx mu by dp dx mu by dp differentiated with respect to p equals dg mu sigma I dx kappa minus gamma minus g mu sigma gamma mu kappa lambda minus g mu kappa gamma mu sigma kappa sigma lambda times dx kappa dp dx sigma dp dx lambda dp. So all we've done is differentiated with respect to p, but we've expressed it in terms of the gammas. And from the definition of the Christoffel symbol, this equals 0. So we conclude that g mu nu dx mu dp dx mu dp equals a constant. Now it's at this stage where we have to discriminate between massive particles and massless particles. If our initial condition is g mu nu dx mu equals ds squared, the proper time. Actually, there's a minus sign issue here. ds squared is the interval in the four-dimensional space-time. But if you're in a minus metric, as we are here, Weinberg calls that tau the proper time with a minus sign. So the constant equals 1 if this is true, which is the case with mass not equal to 0. But we can't use that parameter s or tau for the massless case because this vanishes in the massless case. So we have to use some other parameter. So we can put p equal proper time in the massive case, but p is something, some other parameter. In the massless case. For example, we could be I think Weinberg calls it, check what he calls it, page 87. So make sure I've got the same notation. Well, he calls it sigma. Which is not the proper time. Now, one asks, why is this 0 for a photon? And the argument Weinberg gives is to go to this freely falling frame where you get the special relativistic line element, where it's obvious that ds squared equals 0 because ds squared is c squared dt squared minus dx squared. So if you're traveling at the speed of light, that distance is 0. And then he transforms to the general frame and argues that this is true in general relativity as well. So to get the motion, to get x as a function of time, we don't actually need to know what the parameter is. But if we want to evaluate the proper time in the massive case, then we do. So we'll make use of that in our experimental tests, which we're going to do now. Now, in describing the experimental tests, my notes originally were for those from Anderson. But it occurred to me it might be better to stick, since we started with Weinberg, to stick to Weinberg. And so I'm going to start again. I spent a few minutes yesterday talking about experimental tests. Let's start again using Weinberg's notation. And this is all in chapters 6, I believe, of his book. That's chapter 8, I should say. And he lists 5 at the beginning of chapter 8, page 175. He lists 5 tests that he discusses in this chapter. A is gravitational redshift. B and C are bending of light by the sun and the perihelion of Mercury. And then he's added radar echo delay. And gyroscope precession. I don't think I mentioned this one yesterday, but we did mention radiation, gravitational radiation from binary stars. Now, these have a somewhat different status. We're testing somewhat different things in each case. For example, as we'll see, the first one is not really a test of Einstein's equations in the full sense. It's really a test of the equivalence principle. 2 and 3, or B and C, are tests of Einstein's equations, but they're only testing the Schwarzschild metric. So when we do these experimental tests, the idea, in a way, is to compare what Einstein predicts with what some other rival theory or hypothetical rival theory might predict, and compare the two. So rather than just looking at the Schwarzschild metric, let's look at some more general metrics and then see how Einstein's version is better or worse than the alternative. So let's start looking at other metrics. In harmonic coordinates, it's traditional to write them in like this: 1 minus 2 alpha m over rho. plus 2 beta m squared over rho squared plus higher order terms in m cubed over rho cubed and so on. For the kinds of experiments we're concerned with, rho will always be very much bigger than m. So this is a good expansion, dt squared plus 1 plus 2 gamma m over rho plus d rho squared plus rho squared d omega squared. You could put in the next term here, but it will, when it comes to doing the experimental tests, we'll see that that's higher order, and we can neglect it. Yep.
I thought that harmonic. Well, I thought we.
I'm sorry. Before you ask the question, I wrote the wrong word. Okay.
That we had encountered isotropic coordinates rather than an isotropic metric. If we're seeing other metrics, why is one of them called isotropic?
Okay, the word is referring to the coordinates.
So is this the Schwarzschild metric in isotropic coordinates?
Could you repeat the question?
Is this the Schwarzschild metric in isotropic coordinates?
No, it's not the Schwarzschild metric yet. It's a more general metric that some hypothetical theory might predict that's spherically symmetric without specifying what alpha and beta and gamma are. And we're going to compare that with the Einstein values of alpha, beta, and gamma, which will be the Schwarzschild metric. And we're going to see which of them wins out in the experimental tests. So, but to see what it is in Einstein's theory we're actually testing, it's instructive to put in arbitrary constants and then pin them down later on. In fact, I can tell you now what Einstein says. Alpha equals beta equals gamma equals 1. But you might imagine some other theory that would predict some other values, either existing theory or yet to be discovered theory or hypothetical theory. An existing theory which I may talk about in more detail later on. Let me just mention it now. Goes by the name of Brans-Dicke. Historically, the motive, I think, for the Brans-Dicke theory was an observation of Dirac, that there are certain large numbers in the universe which seem coincidental. And if you were to try and make sense out of them, it would imply that some of the fundamental constants, things that we thought were fundamental constants, were actually changing in time. Now, one has to be careful in this context, and Dicke was careful. He knew perfectly well what he was doing, to talk about dimensionless quantities changing in time, because that's a unit-independent concept. If you talk about dimension-full quantities changing in time, you will get different answers in different units. But sloppily, this is sometimes referred to as variable Newton's constant. It's actually variable dimensionless parameter, but that's what it's usually called. And to do that, they introduced, in addition to g mu nu, a scalar field. called phi. And I'll tell you perhaps in another lecture what the field equations are. Here I just want to remark that this theory has alpha equals beta equals 1, but gamma is different. There's an extra parameter in Dicke's theory, which was omega plus 1 over omega plus 2. Actually, Dicke had another motive, apart from variable Newton's constant, that he wondered whether the sun was as spherical as we think it is. The sun may be slightly oblate, and if it is, you know, it may be more like this than like this. If it were slightly oblate, it would affect the perihelion of Mercury and the bending of light and so on. And Dicke wondered whether one could explain it with his theory better than with Einstein's theory. I can tell you now that these attempts have now been discredited. The sun is not oblate, or at least not significantly enough to alter Einstein's agreement, and the Brans-Dicke theory falls out of favor. However, you can't completely rule it out, because if this parameter is very large, you can't tell the difference between this theory and this one. So when we say we're ruling it out, we're ruling out the small values of omega. But we haven't yet ruled it out. We're being unprejudiced at the moment, allowing alpha, beta, and gamma to be what they may be. Now, in Schwarzschild coordinates, which are more familiar, ds squared equals and these are related to rho by 1 plus gamma m over rho plus dot dot dot, or rho equals r into 1 minus gamma m over r, if you prefer. Then this becomes 1 minus 2 alpha m over r plus 2 beta minus alpha gamma m squared over r squared dt squared plus 1 plus 2 gamma m over r dr squared plus r squared d omega squared. Now we're going to come back to that in just a moment. For now, we're going to call these functions a and b. And we're going to write the line element minus b of r dt squared plus a of r dr squared plus r squared d omega squared. So we're going to leave A and B arbitrary functions and then plug in their values later on. So consider a freely falling object or it could be a particle or it could be a photon. Obeying d mu x mu dp squared plus gamma mu rho sigma dx sigma dp dx rho dp equals 0. Then, using the gammas that Weinberg gives us, which I won't bother to calculate explicitly, they're in section 8.111, I believe. These reduce to equations for r, theta, phi, and t. The r equation is d2r dp squared plus a prime over 2a dr dp all squared. Prime is d by dr. That's the r equation. The theta equation is d2 theta by dp squared plus 2 over r d theta by dp dr by dp minus sine theta cos theta d phi by dp squared. The phi equation is d2 phi dp squared plus 2 over r d phi dp dr dp plus 2 cotangent theta d phi dp d theta dp. And finally, the t equation now, I think I did this yesterday and there were some questions about it, but we're going to put theta equal pi by 2 without loss of generality, because the orbits will lie in a plane. And I guess if you could solve, rather than doing that now, you could leave theta unfixed and discover from the solution that that is the case. But either way, that solves the equations. And it's a constant of the motion, I guess, is another way of saying it. It follows from the equations that the orbits lie in a plane. And that's what we observe. Planets don't go like this. They orbit the sun in a plane. And when a photon passes the sun, it lies in the same plane.
So we could, what you're saying, that we could find out that theta is a constant if we began by letting it vary and then found in the solution that theta is constant. But
Yeah.
Weinberg's explanation was that theta is constant because the gravitational field is isotropic. And
when I say we would discover that theta is constant, I mean when we plug in this metric. Wouldn't be true for arbitrary gravitational fields.
I just meant, so there are two reasons, well, at least two reasons to accept that theta is constant. One is by substituting into the metric and solving, and then finding at the end of all this that theta is constant, or Weinberg's path toward understanding why theta should be constant seems to be a physical consideration, namely that the gravitational field.
Well, it's a shortcut, yeah.
Yeah, so I'm not sure why the knowledge that why the isotropic nature of the gravitational field should cause theta to be constant but not phi.
Well, phi is the amount of phi is telling us how much is going around the sun. Looking at it from this way, theta is telling us whether it does this or whether it does something like this. And what Weinberg's saying is that it lies in the same plane because the field is isotropic.
I'm just wondering why isotropic nature of the field should
But it doesn't.
determine one but not
Phi,
the other.
phi, you don't want phi to be constant because then it wouldn't orbit the planet.
Well, I see that, but how does that not follow from? How does phi not constant? How does phi varying
Well,
with theta not varying? How do both? How does one follow from gravitational field isotropic and the other not?
well, you could, as I said, I think, solve the equations, carry on solving the equations, leaving theta undetermined, and you would discover theta dot 0.
Wanted to try to get there by Weinberg's.
And Weinberg's physical intuition says, well, we're going to get that anyway because an isotropic field wouldn't give rise to that kind of motion. If you don't find it convincing, I guess you could do it the long way. But it's just a shortcut.
I'm wondering why it's a shortcut to that end. Okay.
So now we divide. That'd be useful to number these equations. I was in the right place to start with. So this is equation 1. This is equation 2. This is equations 3 and 4. These are equations 5 and 6. So we divide 5 and 6 by d phi dp. And dt dp. Respectively. And we get d by dp log d phi dp Okay, I was wondering where equation 7 went. There's that one. Okay, so this is equation 8. D by dp log d phi dp plus log r squared is equal to 0. And d by dp log dt by dp plus log b is equal to 0. It's equation 9. And this is interesting because it yields two constants of the motion. And he chooses a normalization dt dp equals 1 over b. And then 8 becomes r squared d phi dp equals a constant, which we call j. And which will have the interpretation of angular momentum. Plugging 7 this is equation 10, equation 11. Plugging 7 into 7, 10, and 11 into 3, 3 was over there. Gives 0 is d2r dp squared plus a prime over 2a dr dp squared minus j squared over r cubed a plus b prime over ab equals 0. And we multiply by 2a dr dp to get d by dp a dr dp squared plus j squared over r squared minus 1 over b is equal to 0. So we have another constant of the motion, namely a dr dp squared plus j squared over r squared minus 1 over b, and we're going to call that E or minus E. And that's going to be associated with energy. And it implies in particular that ds squared is minus E dp squared. And E is going to be greater than 0 for massive particles and equal to 0 for photons. That's equation 13, 14, 15, and 16. So what we've discovered is that there are, whether we're talking about planets going around suns or photons being bent by planets, either way there's constants of the motion involved, J and E. Now, in practice, A is going to be positive because we're far away from the center of the sun or whatever it is. And that gives us an inequality it tells us that j squared over r squared plus e squared plus e cannot be less than greater than 1 over b, less than or equal to 1 over b. Now, at the beginning of the talk, I mentioned that we didn't need to know what this parameter p was. We could eliminate it. And that's what I'm going to do now. And what we get is a over b squared dr by dt squared plus j squared over r squared minus 1 over b is equal to minus e.
remind us of the significance of A being greater than 0?
A is 1 minus 2n over r in Einstein's theory, or something similar in the generic theory. And since r is very much bigger than the celestial radius in these solar system tests, A will be positive, bigger than 1. Bigger than 0, sorry. Is there another question? Yeah.
Why there's no dependence on T for the B, the big B?
Well, Birkhoff's theorem is the answer. You may remember we proved that spherical symmetry was enough to guarantee static solution in a previous lecture. Pardon? We are assuming spherical symmetry, that's correct, yes. And apparently this tells us ds squared is EB squared dt squared. Now, for slowly moving particles, and compared to the speed of light, Mercury would be regarded as a slowly moving particle. In a weak field, J squared over R squared, dr by dt squared, A minus 1, B minus 1, which is approximately 2 phi, will all be small. And to first order, we have r squared d phi dt is approximately equal to j, which is the Newtonian expression, and a half dr dt squared plus j squared over 2r squared plus phi is approximately 1 minus e over 2. Which is again like Newton with 1 minus e over 2, the energy per unit mass. Now, this is an equation for the planet going around the sun. I should have drawn that at the... Oh, I'm sorry. Which bit can't you read? After? Energy per unit mass? Like Newton, with 1 minus e over 2, the energy per unit mass. I'm sorry if I'm writing behind the screen there. Would you like me to rewrite it? I've made the same mistake that the Bank of England made when they put the Earth at the center of the ellipse on a banknote. It is, of course, at the that's where the sun is. What we've calculated is r as a function of t, which is interesting, but it's more useful to calculate phi as a function of r. So we can do that. So instead we can eliminate P from equations 11 and 13 to get A over r to the fourth dr by d phi squared plus 1 over r squared minus 1 over j squared. B is minus e over j squared. So we can integrate this to get an expression for phi, a to the 1/2 dr over r squared to 1 over j squared b minus e over j squared minus 1 over r squared to the 1/2. So that was a lot of work, but we've got the answer we want. We've now got phi, the azimuthal angle, as a function of the radial coordinate. And that's what we need to look at the perihelion of Mercury. We'll do that tomorrow, but let me just give you a flavor of what's happening here. In Newtonian physics, according to Kepler's laws, the planets orbit the sun in a perfect ellipse. So if you start out here, 2 pi phi later, it comes back to where it was before. And the point of closest approach, the perihelion, is the same every orbit. Now, what was observed, and what was something of a mystery until Einstein explained it, was that the planet Mercury, probably not drawing this very well, does not describe as a perfect ellipse. Instead, it comes back, and its point of closest approach has gone forward a little bit. And the next time around, it would have gone forward a bit more, and so on. Now, it's very tiny, that angle is a few seconds of arc per century, so it's not a massive effect. And it's even smaller for the other planets. It's biggest for Mercury because it's closest to the sun. Nevertheless, Einstein's theory predicts, as we'll see tomorrow, that this should happen, and we can calculate delta phi, and we can compare it with experiment. And that's what we'll do tomorrow. Thanks. See you tomorrow.